Hello and welcome to the proof that the reals are uncountable. All right, so what does countable mean? So countability means that we can make what's called a bijection, which is a function that goes from one domain to the codomain, and it is going to be one-to-one and onto. And in the terms or in the when we're talking about countability, what we want is the naturals over here to map to something else, right? Or in this case, the naturals. The naturals are countable, and also the integers are countable, and the rationals are countable. And we've seen this one before, but just to sort of go over what a proper bijection should look like, if we have these two little shapes here, and this is our naturals, let's say, and this is our something else, we want to be able to have every element mapped to every other element. So notice that none of these get left out. All four of them are sort of in here, and all of these go somewhere, right? So no two elements in the naturals are going to map to the same place, right? And that's injective. And then the surjective is that all of these elements are sort of hit when we are mapping, right? So they're all getting hit here. If this went over here instead and this guy was left out, then it wouldn't be surjective and it wouldn't be a bijection. All right, so what does uncountable mean? A little bit of history for you. This is George Cantor, not Jorg, just George. And so he was the one that sort of came up with even the concept of countability, right? Because before that, all sort of concepts of infinity were viewed as the same size. And nobody had really thought about an infinity that would be bigger than another one, because it's sort of a difficult concept to think about. Like, what do you mean something that is infinitely large is not as infinitely large as something else? Sort of hard to wrap your head around. And he was able to sort of get rid of the belief that all of these infinities were the same. And he came up with his first sort of indirect proof of the uncountability of the real numbers in 1874. And nobody liked it. Everyone thought it was sort of bad math. They thought it was offensive. A popular mathematician at the time, Leopold Kronecker, said that God made the integers, all else is the work of man, in response to Cantor's proof, literally saying it's ungodly math, which is pretty mean. I think I wouldn't like that if someone wrote that on one of my proofs. Please don't write that in the comments. So without further ado, let's get this set up. It's going to be a proof by contradiction. So we're going to assume that R is countable, meaning we can create a bijection f, that so this bijection function that goes from the naturals and it goes straight to the reals, and it's going to be one-to-one and onto. Bit of an issue here though, and it's that R is really big. It's dense. So instead of doing all of R, we're going to look at just in between 0 and 1. So our new goal is to find a bijection that goes from the naturals to the interval 0 to 1 in the reals, right? So it's still a subset of the real numbers, but just to sort of make everything a lot nicer, we're going to just do the interval 0 to 1. If we can make a countable, if we can do this mapping, then there's some theory that allows us to sort of just do this larger mapping over here. And that has to do with how R is dense, or the reals are dense. So without further ado, let's start our bijection. So in the left column over here, I've got all of these natural numbers. This is just straight up counting up. We've hopefully seen this before. And then we do a little skip here, and then we get to some n plus 1, and then we just keep going forever. And then over here, I've got just a random assortment. Really no rhyme or reason. I tried to make these fairly random. And these are just a bunch of numbers that happen to be in between this little 0 to 1 interval. Starts with like 0.34. I've got 0.994. I've even got just 0.3 over here, and then these are zeros. The little dots here are just to sort of show gaps, and just a reminder, all of these decimals are repeating. They could be repeating zeros, right? Like this is just 0.3. We don't really have to think about this bit, but for the purposes of our proof, we're gonna just represent these all as repeating decimals. This one is 0.8 repeating, so this is just going to be a bunch of 8s at the end. For example, this number here could be 89112, and it's gonna go forever. And these are just real numbers. So how do we sort of disprove this mapping? Because right now, to me, it looks pretty good. I've got a number associated with 1, I've got a number associated with 2, and I don't have any repeat numbers here, right? Like I don't have 0.88 repeating again. It only shows up once, and it's only associated with this n. And yeah, so everything sort of seems all in order. And this is part of our assumption that all of these natural numbers correspond to all of these real numbers. And this sort of is starting to look like a bijection. Okay, it's very nice. Until Cantor figures out a way to disprove this, which other famous mathematician Poincare said was a grave disease, another truly devastating thing for someone to say. So to disprove this, we're gonna make some rules. So rule 1 is we're going to travel along the diagonal. Rule 2 is that we are going to set this: if a number is less than 8, we add 1 to it. And by a number, I guess it should be a little bit more specific. I'm talking about a number in a digit space. So something like 1, 2, 3, 4, 8. Right? If I encounter this and I consider that sort of my number that I'm looking at, that's less than 8. So I'm going to turn that into a 4, if that makes any sense. And then the last rule is if a number is greater than or equal to 8, we subtract 1 from it. So if I come back and I'm looking at this guy right here, that's an 8. So I'm going to turn that 8 into a 7. And you may be sort of thinking, what are you talking about? Like, how is this all going to work? So let me show you. First off, we're going to follow rule 1 and travel along the diagonal. So to make it sort of easier to see, I'm going to just highlight the numbers I'm talking about on the diagonal. Okay, so these are the numbers we're looking at. And following our rule, if a number is less than 8, so let's just start with this 3 up here. So this 3 is less than 8, and I'm going to just start writing our new numbers down here. And we're starting with 3. Remember that these are all sort of in the same interval. So I don't want this to be bigger than 0. So the first one we had was 3, so I'm going to add 1 to 3, and I get 4. And go back up, and I've got a 9. So we're going to take that 9 and subtract 1. That's going to give us an 8, because 9 is going to be greater than or equal to 8. Then I've got 1, 0, 0, 4. I'm going to do these all at once. So starting with 1, going to add 1 to it. That makes a 2. I've got 0, 0. So we're going to go 1, 1. And then I've got a 4. We're going to turn that into a 5. And our last 2 are going to be 8 and 8. So that's going to be 7. We subtract 1 and 7. So what does this new number sort of tell us? And what did we really do? Well, we actually disproved this bijection. Why is that? Well, if you'll allow me to just sort of yank this number, and we'll throw it on up here. So in this number just is not in our mapping. And it sort of gets easier to see once we think about how we are counting all these numbers. So in the ones place, where we have 1, we know it's not there because we changed that first digit to 4. And we know it's not 2 because we changed that second digit to 8. We know it's not going to be this 3 because we changed this third digit to 2. We know it's not 4 because we changed this fourth digit to 1, and so on and so forth. All of these are different. And these little dots here, right? We're still following the rules in these. If I wrote another 6 or 7 numbers here, we're always gonna either add 1 or subtract 1, which makes it different than the number that we are talking about. For these random nths, right? We know it's not either of these because all we have to do is check the nth digit, and it's an 8, and we change the nth digit to a 7. This one was an 8, and we changed that n plus 1th digit to an 8. And we would keep going with this. This doesn't end. For sort of all the natural numbers, we know that this number is not in it, which means if we sort of think back to our bijection, right, where we had these 2 little blobs, if you will, and we have a bunch of numbers here, they all map really cleanly to different numbers in our codomain. Maybe I shouldn't have had so many. Hold on. So let's say I just have 3, right? And these 3 represent all the natural numbers. And so they're hitting this one over here, right? Which is our sort of, these guys over here are these numbers, and these numbers here are these little dots. And what we've just done with this number is we've actually shown there's another number in here, and this never gets mapped to anything. We know that because we made sure that for all of these natural numbers, this number never shows up. And this is a real number. It's sort of really easy to think about. It just because sort of all numbers are going to fall into the real number category unless we insert an I in here, which we certainly didn't. That wasn't part of our rules. And this means it's not surjective, which then, therefore, our claim that our function, our bijection from n the naturals to this interval in the reals is false. So therefore, the reals are uncountable. And that was Cantor's quote unquote ungodly proof or nonsense proof. Back to Kronecker, he said that it was actually corrupting the youth. So if you feel corrupted after this proof, I've hopefully done a good job. But really quick before I end the video, I'm going to talk about why we subtract when we see an 8 or a 9. So let's say we have some number and it's 8 repeating. In fact, if you look above, I did have 8 repeating. This guy right here. And let's say all of a sudden, at some point, we start having 9 repeating. Now, if I was following my rule, and I went in and I'm sort of going along my diagonalization, and all of a sudden I get to this 8, and I change the 8, changing this 8 to a 9. What have I done here? Just fill this back in with a bunch of 8s. With a bunch of 8s. Well, so what I've done is I've actually made a completely different number. These 9s are repeating, and the issue that I might have is that I've actually just created a duplicate number, because these 9s repeating means that this is actually, if I can keep this lined up, 2, 3, 4, 5, 6. This is actually this number. These are the same. And I will hopefully demonstrate this with this little fun proof that 1 is the same as 0.999 repeating. So go about doing this real quick proof. We're going to set this to A. And we are going to say that we're going to look at 10A. What does that equal? Well, if you multiply something by 10, we're just going to pop this decimal over 1. So we get 9.9999 repeating forever. And then now I'm going to subtract 1 from A, or 1 from 10A. So I'm going to go like this, minus A, minus A. And what do I get here? Well, I get 9A is equal to, and if we think about what A is again, this is 0.9999 repeating. All of these 9s get canceled out, and I get that 9A equals 9. Dividing both sides by 9, I get that A equals 1. But we said that A equals 0.999 repeating, so they are equivalent. So if we are doing our little diagonalization, what this can do when we change an 8 to a 9 is we actually create a different number that might have already been in our big list of numbers, right? It might have already shown up, and we really, the whole proof hinges on the fact that we don't make a number show up again. Right? We can concretely say, like when I made this number here, that it was fundamentally different than all of the numbers that have come before it. If all of a sudden I made, I had a number that was like 28999, and I changed this guy to 9, and I'm just following my normal diagonalization, but all of a sudden this number right here, that's the same as this guy up here. That's just 0.3, assuming these 9s are repeating. So it would sort of break the whole proof down. We couldn't actually say that this number does not have a, that's the wrong symbol. this number is just not in here, right? And that's sort of all what the sort of punchline of our proof is. And so that's why it's really important not to change eights to nines. But what about nines to, why do we subtract from nines? So for a similar reason, if I have a number like 3, let's just do 0.3900000 repeating. Okay. So I know that I'm doing my diagonalization, and all of a sudden I get this 9. And I change that 9 and I increase it by 1, right? That and let's just call that, this is either going to be 4000 repeating, or I could also consider it, depending on how I'm viewing, if I'm talking about like integers mod 10, or if I'm just straight up adding what is this, 100th. Could either be these two. Obviously I have to keep the rule consistent, but either one of these causes problems. Why does it cause a problem? Well, for the same reason above, these two numbers, I don't know if they showed up. Right? These are definitely numbers that I could have written before. And for that reason, it sort of also breaks down our big proof that if this is what I end up with, all of a sudden, maybe this number is in my list of my mapping of the naturals to the reals. Maybe it's not, and I can't tell. Therefore, I can't really do my proof. And yeah, so that's sort of an explanation on why we have this little subtraction rule. Once again, thank you for watching, and I hope that my proof of the reals being uncountable was easy enough to understand, and hopefully not too much of a grave disease.